We started dealing with discrete probability distribution. We covered probability distributions, binomial probability distributions, and we're going to briefly go over Poisson probability distribution. First, the idea of probability distribution, understanding the concept of a random variable and probability distribution. Probability distribution, when it comes to discrete random variable, in essence, it's mainly a table containing the variable x, the random variable x, and the probability of that. So basically, it's a table containing the two columns. X, the random variable, must be numerical. Probabilities, they must add up to 1, and each one must be between 0 and 1. And we have the formulas for a general case of a discrete random variable. Mu, the expected value, is the summation of xp of x, and the standard deviation. There are a couple of different ways of calculating. We first calculate the variance, summation of x squared times p of x, and we add them up. When we're done, we subtract mu squared, or we calculate x minus mu squared times p of x, we add them up. That would be the variance taking a root, results in finding standard deviation. In the case of a binomial distribution, first it is important to understand how we arrive at it. The main thing that we need to be concerned with in case of a binomial distribution is that there are two categories. There are two outcomes, if you will. Now, everything else should happen, meaning we have n identical trials, and probability stays constant from one stage to the next. And they are independent trials. In many cases, we can assume that, or they are actually independent. So the main thing you want to pay attention is that there are two outcomes, in which case the parameters become two things, n and p. The moment you recognize it's a binomial distribution, you have to be able to come up with the value of n and p, which is known as the probability of success. And then the formula is very straightforward. The probability of x is combination of n choose x, p to the power of x, q to the power of n minus x. The mean, or mu, is equal to np, and sigma is square root of npq. Now, let's go to Poisson probability distribution. In this section, we look at Poisson probability distribution. It's a different category of discrete probability distribution.
A Poisson probability distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval. The random variable x is the number of occurrences of the event in an interval. The interval can be time, distance, area, volume, or some similar unit. The probability of the event occurring x times over an interval is given by p of x is equal to the mean to the power of x times e to the power of negative mu over x factorial, where e is equal to 2.71828 and mu is equal to the mean number of occurrences of the event in the intervals. The parameters are mu and sigma, which are equal to the square root of mu.
One thing I want to add, of course, e, just like pi, okay, it's an irrational number. And when you use a calculator for the sake of calculation, you keep it as e, and it gives it many decimals. So pi 3.1415, and it continues indefinitely. So, but I wanted to mention e is not missing, okay, e is not a variable, e is a number. In some text, instead of mu, they use lambda. If you look at the bottom right, and I'm showing you how to use a TI calculator for lambda, instead of mu is used. And as far as the parameters, if you remember, for the binomial distribution was n and p, in this case is mu and sigma, where sigma is square root of mu. In essence, when mu is given, then you can handle the Poisson distribution.
Properties of the Poisson probability distribution. The particular Poisson distribution is determined only by the mean mu. The Poisson distribution has possible x values of 0, 1, 2, with no upper limit.
And the requirements?
The random variable x is the number of occurrences of an event in some interval. The occurrences must be random, and the occurrences must be independent of each other. The occurrences must be uniformly distributed
over the interval being used.
And so let's look at this example.
For the 55-year period since 1960, there were 336 Atlantic hurricanes. Assume the Poisson distribution. A. Find mu, the mean number of hurricanes per year. B. Find the probability that in randomly selected year, there are exactly 8 hurricanes. Find probability of 8, where P of X is a probability of X Atlantic hurricanes in a year. C. In this 55-year period, there were actually 5 years with 8 Atlantic hurricanes. How does this actual result compare to the probability found in Part B? Does the Poisson distribution appear to be a good model in this case?
Mu, by definition, it's done uniformly, the number of hurricanes over the number of years. We calculate that. We divide 336 hurricanes over the course of 55 years, and we get 6.1. If we were to give it a unit, the units would be 6.1 hurricanes per year. The units also follow the methodology of operation we use. So in this case, it was the operation of division. So the units of the numerator over the units of the denominator. Finding the probability of 8, that means X is 8, and we already have mu. And by the way, I'm again writing E equals 2.71828, but you really don't have to. It's just E, and your calculator has that. So I would highly recommend you stick with E. That gives you a better approximation. And now we put it into the top formula in red. P of X is mu to the power of X, e to the power minus mu over X factorial. So P of 8 would be mu, which is 6.1, to the power of X, which is 8, e to the power of negative mu, which is negative 6.1 over X, which means 8 factorial. And now it's just a matter of using a calculator, and we end up with the answers. So there were actually 5 years with 8 Atlantic hurricanes. So let's see what happens if we want to look into that. The probability of 8 is 0.107, almost 11%, to get 8 hurricanes in 1 year over the course of 55-year period. And the expected value is the same thing times 55. So 55 times 0.107, remember, the expected value in essence is X P of X. That's really the formula in the discrete random variable concept that was used before. So there are 55 years, and the probability is 0.017. The product is the answer, and it ends up being 5.9 years. So the expected number of years with 8 hurricanes is 5.9, which is definitely reasonable because it's extremely close to number 5. So Poisson distribution fits perfect. Now, as far as Poisson distribution is concerned, if you were to use a calculator in some text, and as far as the calculator and technology is concerned, instead of mu, they may use lambda, and you may see that in some other text. So lambda or mu is 6.1, X is 8. So you use the methodology that was discussed in the previous page, second variables, then you go to Poisson Pdf, and you put those two values, you enter, and you get to the answer. If you do the rounding, the answer is 0.107.
In analyzing hits by V1 buzz bombs in World War II, South London was subdivided into 576 regions, each with an area of 0.25 kilometers. A total of 535 bombs hit the combined area of 576 regions. If a region is randomly selected, find the probability that it was hit exactly twice. The V1 buzz bomb was the world's first operational cruise missile, a small unmanned airplane with an autopilot and a cutoff device. Note the Poisson distribution applies because we are dealing with occurrences of an event, bomb hits, over some interval, a region with area of 0.25 kilometers squared.
We need to calculate the mean. So the mean, which represents the number of hits per region, is the number of bombs per the number of regions. So we do the division, And 535 divided by 576 gives us 0.929 of hits per region on the average. Now we go to the top right formula in red and we plug in x is equal to 2, and we just found the value of mu. So using this formula, we just plug in to calculate P of 2. Remember, twice. I want you to see where number 2 comes from, okay? Exactly twice, P of 2. And so we plug in, and the calculator gives us about 17%, okay? So that would be the answer for the question. The probability of a specific region being hit is about 17%. Being hit how many times? Twice. The next thing we want to look at is Poisson distribution as an approximation to binomial. It used to be that a lot of calculations couldn't be done and tables were used. Now technology makes it easier, therefore there is no need for that. I will discuss the table as we come across the normal distribution. And because the binomial distribution is sometimes very difficult to do it by hand, the statisticians have been using other methods to get the binomial distribution. So they use approximation to that. For example, we have normal that approximates binomial. Now this one is Poisson distribution that can approximate the binomial. And Poisson distribution can approximate the binomial distribution as long as we have number 1, n is large. How large is large? Larger than or equal to 100. And then np is less than or equal to 10. Okay, that is, again, what statisticians have come up with. If that is the case, then we can approximate it using Poisson distribution, and mu is np. As you recall, in the case of a BD, binomial distribution, mu was np, sigma was square root of npq. So with that being the case, let's quickly look at an example of that.
Assume that in a pick 4 game, you pay $2 to select a sequence of 4 digits, 0 to 9, such as 1255. If you play the game once every day, find the probability of winning at least once in a year with 365 days.
What I want everybody to pay attention to is that when we say pick 4, that means those are 4 digits and there is no restriction. Any number will do as long as there are 4 digits. That's the idea behind pick 4. And so what we are dealing with, it is a binomial distribution with n being 365 because we are talking about 365 days. And why is it a binomial distribution? The main thing that makes it a binomial distribution, there are 2 outcomes, winning or not. So 2 outcomes, you're dealing with a binomial distribution. The probability of winning is 1 over 10 to the power of 4. Why is that? Because there are 4 digits. Each spot, you get 0 to 9, 10 possible outcomes. So there are 4 of them. 10 times 10, how many times? 4 times. So the probability of winning is 1 over n of winning over n of s, 1 out of 10,000. So you're dealing with binomial distribution, and you can do binomial distribution. However, as the bottom says and repeats the concept of a previous page, Poisson distribution is sometimes used as an approximation where n is larger than or equal to 100 and np is less than or equal to 10. So let's look at the requirements and the conditions discussed. N is larger than 100 because n is 365. And then np, let's multiply the n, 365, by the probability of winning, which is 1 out of 10,000, and it's less than 10, so that will do the job. Let's go with the Poisson distribution. To do so, everybody remembers the probability of at least 1, probability of at least 1 or at least once in this case, means the probability of x equals 1, x equals 2, all the way to n, and happened to be 365. And the easiest way was to write it as 1 minus the probability of none. So we go that route. So that means we calculate probability of none or probability of 0, and whatever the answer is, we subtract it from 1. With that being the case, let us use this Poisson distribution, plug in the values accordingly for x being 0. And remember, 0 factorial is 1. Anything to the power of 0 is 1. And so we end up with 0.9642 for the probability of 0. Now, take a look at binomial PDF. If you use your calculator to come up with the binomial PDF, look at the number, and again, you can use a calculator. I've given you the result of that here. If you compare it, you see that it's almost identical. If you use Poisson distribution, it's almost identical. And I hope you see how close the two are. And then 1 minus that is the answer. Again, I want you to see these two are the same, okay? But that's not the answer. The answer is 1 minus 0.9642. The next topic is about, in essence, continuous random variable. So normal probability distribution, starting with the standard normal distribution. And then we continue on with the application of that, sampling distributions and estimators, the CLT, central limit theorem, assessing normality, and normal as approximation to binomial. We just looked at Poisson distribution as an approximation. Normal is used also, and it's used a lot more often. So the objectives, we're going to identify distributions as symmetric or skewed. We will look at properties of normal distributions. We want to find the area under standard normal distribution. I'm going to use SND for short, given various C values, finding probabilities for normal distribution, and transforming them into standard normal distribution using the Z. Specific data can be found using the concept of a percentage, use the central limit theorem, and use the normal approximation to find binomial distribution. Let's actually start with 5.1. We looked at discrete random variable in general, and the main thing that we need to know is that the variable x must be numerical. The total probability is always 1 or something extremely close, because sometimes we get round of error. We got to be very careful with that. And the probability is always between 0 and 1. It's never negative. It's never larger than 1. Binomial distribution, among other requirements, the main requirement we got to pay attention is that there are two outcomes. As long as we have n identical trials, they are independent, the probability doesn't change. When we say probability stays constant, that means from one stage to the next doesn't change. For example, if you are dealing with tossing a coin, the first stage, the probability stays constant as 50-50, the second one and the third one, and so on. Even if it happened to be a loaded coin, let's say the probability of heads is 60% and tails is 40%. If you're using the same coin, the second stage and the third and so on and so forth, the probability stays the same. And that's the idea behind binomial distribution. And then for Poisson distribution, it uses a specific formula. As I mentioned, we may use mu or lambda to represent the expected value. Okay. The probability of the event occurring x times over an interval, we can use a Poisson distribution. And it is also a discrete distribution that we need to pay attention to. Now, the requirements is that the random variable, of course, happens over an interval. It is random, it is independent, and it is uniformly distributed. Now, standard normal distribution.
If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it has a normal distribution.
Key concept: the standard normal distribution is a specific normal distribution having the following three properties. 1. Bell-shaped. The graph of the standard normal distribution is bell-shaped. 2. Mu is equal to 0. The standard normal distribution has a mean equal to 0. 3. Sigma is equal to 1. The standard normal distribution has a standard deviation equal to 1. In this section, we developed the skill to find areas or probabilities or relative frequencies corresponding to various regions under the graph of the standard normal distribution. In addition, we find z-scores that correspond to areas under the graph. For a continuous random variable, the probability of a single value of x is always 0.
Normal distribution, we really have to pay attention to those three. If you're claiming something is a normal distribution, you have to come up with parameters mu and sigma. Okay, and it happened to be mu happened to be 0 for SND, standard normal distribution, and sigma happened to be 1 for SND. And this is what is used for the concept of z-score, if you will. So a z-score of 0 means the number is equal to the average. Concept is extremely important. It doesn't mean that horrible. On the other hand, if it's negative, it means below average. The thing that I want to add, and this is important, any continuous random variable, when that happens, the probability of a single value is always 0 because it doesn't cover any area. Now, if you look at the formula at the top right, it gives the mathematical equation for the normal distribution. Y is equal to e to the power of minus parentheses x minus mu quantity squared over 2 sigma squared, and the whole thing over sigma square root of 2 pi. Sometimes they write it as y equals 1 over sigma square root of 2 pi e to the power of minus x minus mu squared over 2 sigma squared. This is the equation for this curve, for this function. And this function, the total area under the curve represents the total probability, and therefore it's equal to 1. Of course, pi is a constant. Sigma and mu will be given to us, and that gives rise to the function that you can see. And when they want to calculate the probability, they have to calculate the area under the curve, which requires calculus. That's why you're given a table, or you can use a calculator or any other technology. But understand the concept is the area under the curve is calculated using calculus and the integral of a to b f of x dx. Just in case if anybody is familiar and comfortable with calculus, that's the concept. Now, that's a general curve. As you can see, it's bell-shaped. As you can see, it's symmetric, and it's symmetric about mu. Now, if this represents probability, the total area must be 1. If this represents probability and it's symmetric, on each side, the area must be 0.5. It is extremely important to understand this concept. If you're interested in reading tables, you really need to know how this thing works. Again, the whole area is 1. Why is that? Because it represents the total probability. Because of the symmetry on each side, we have an area of 0.5. Now, when we look at these curves, remember the total area under the curve must be 1. Okay? So for example, if you have the same means, mu1 is equal to mu2, smacked in the middle. If sigma is larger for one of them, in this case, sigma 1 is larger than sigma 2. For the blue one is sigma 1. So it spreads longer than the other curve. The other curve, they are closer to mu. Remember, the total area must be 1 and it doesn't change. In this case, we have different means, different standard deviations. So if you compare this to the very first one, in essence, you're looking at the same curves, but one has shifted to the right because they don't have the same mean. That's the idea. The mean may be different, standard deviation may be different. In this example, if you see the shape is identical, it's just that the means happen to be at different points. So that's a concept that you want to pay attention to. All of it comes from the fact that the total area under the curve represents the total probability of 1. Normal distribution is bell-shaped, bell-shaped. The mean, median, and mode are equal and located at the center of the distribution. The normal distribution curve is unimodal. It has only one mode.
The curve is symmetrical about the mean, which is equivalent to saying that its shape is the same on both sides of a vertical line passing through the center. The curve is continuous, i.e. there are no gaps or holes.
The curve never touches the x-axis. Theoretically, no matter how far in either direction the curve extends, it never meets the x-axis, but it gets increasingly closer. The total area under the curve equals 1 or 100%.
Finally, the empirical rule that we discussed, and When we start from the mean, we go one standard deviation away on each side. It covers 68% of the data. Two standard deviations away covers 95%. And three standard deviations away covers almost everything, which is 99.7%. That's important to see that comes from this graph. And if you look up the table or if you use technology, you can easily see these numbers. In fact, that 95% is an approximation. It's 95.4%, just to give you an idea. Or that 68% is about 68.26%. All right, empirical rule, we had seen it before, nothing brand new. A uniform distribution is also a continuous one. So a continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. So it ends up being a rectangular shape. Properties of uniform distribution.
1. The area under the graph of a continuous probability distribution is equal to 1. 2. There is a correspondence between area and probability, so probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle. Area is equal to height times width.
The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1.
Density curve, area is 1. So because the total area under any density curve is equal to 1, there is a correspondence between area and probability.
JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes. All of the different possible waiting times are equally likely. Waiting times can be any value between 0 and 5 minutes. It's a continuous value. So it is possible to have a waiting time of 1.23456 minutes. Find the probability that a randomly selected passenger has a waiting time of at least 2 minutes.
When we look at this case, we can, by the way, do the drawing on our own. You basically have a horizontal axis. X represents the waiting time in minutes, and you have the vertical axis P of X. It's important to know that because it's going to go from 0 to 5, if the total area under the curve is 1, we can find the height, which represents the probability. So the very first thing we need to understand, the area is 1, and the width from 0 to 5 is 5. And so what is the height? The height would be the reciprocal of that. Why is that? Because the product of two numbers that are reciprocals would be 1. So the answer is the reciprocal. How do you find the reciprocal? Very simple, 1 over 5 or 0.2. That is the height. That is the probability, if you will, in general, which is a uniform case. So what is the probability of wait time that is at least 2 minutes? That means, so this is 2, and we want at least 2. That means larger than 2. Area under the curve represents the probability of interest. So probability of at least 2, probability of X larger than or equal to 2. We need to calculate the area, this simple case. The height is 0.2. From 2 to 5, that means 3. And there you have it. So the probability of at least waiting for 2 minutes is about 60%, according to this. So that's a uniform distribution. As it was mentioned before, standard normal distribution, we're going to use SND for short, has the following parameters. Mu is 0, sigma is 1, and when you ask an instructor whether they're going to curve the grade or not, you are referring to this curve z-score. We discussed the z-score as x minus mu over sigma, and to come up with the answer, we can use the z-table or we can use a technology. To the left of a z-value, we can look up a z-value in the table and use the area given. Now, the z-score may be negative or positive. Again, I can't emphasize this enough. The z-score is negative. Let's say a student has a z-score of negative on their first exam. It doesn't mean the exam score is negative. It's just the exam score is below the average. Or a z-score of 2. That means it's 2 standard deviations above the average. Now, to the right, look up the z-value and subtract the area from 1. Now, one of the things that happens when you want to look up a table, if you get comfortable with that and you remember the concept of a symmetry, this is really referring to the table here. The tables are different in different texts. In some texts, the tables go from 0 to infinity, and you have to adjust for it accordingly. Most of the texts nowadays, they have the z-table for negative values and the positive values. They have made it easy for the students. And by symmetry, the area to the left of a negative value of z is the same as the area to the positive value of z. And sometimes one may be easier than the other to look up. And I mentioned that as we come across it in a moment. And if you want it to be between two values, such as this one, look at the graph. The graph is extremely important. So between two z values, look up both z values and subtract the corresponding areas. So that's how it's done. Let's look at a very simple example to get us started. We are trying to just get comfortable with reading tables.
A bone mineral density test can help identify the presence or likelihood of osteoporosis, which is measured as a z-score, and the normal distribution. So mu is equal to 0 and sigma is equal to 1. Question: a randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density score less than 1.27.
So we want to see how this is done. So here's the graph. Notice mu equals 0 happens in the middle, 0.5 on the left, 0.5 on the right. And you look at z equals 1.27. What I want to mention is that number 1.27, when you do the drawing, it may not be to scale. It doesn't matter. By looking at it, I hope you realize the answer must be larger than 0.5. Why is it important that you realize that? Because if you're looking up a table or you're using a calculator to get to the answer, and the answer is less than 0.5, you should recognize it can't be right. So how do we look up a table? Here's the portion of a table known as a z-table. So I want you to pay attention to the way we read that. If you look at a z-table, on the left column, you read the number which has 2 digits, 0.2 for example. So it has 1 decimal. The second decimal comes from the top row. So we want 1.27. How do we locate that? The left column gives us 1.2. The top row gives us 0.07. And the two result in the answer 0.8980. 0.8980. This is reading the table. I will discuss the calculator in a moment, but in general, we should be able to read the table. And this is a positive z-score, by the way. And here's the interpretation: the probability that a randomly selected person has a bone density test result below 1.27 is about 89.8%. Okay, we'll conclude that 89% of people have bone density levels below 1.27. That was dealing with the table. Now this table, you can find it on Canvas. So this is the negative z-score. As you can see on the left side, you see the negative z-score. And at the top, you have the second decimal. And there are a couple of asterisks with the arrows. Let's just show the answer. Those are some common values. So if you look at the first one, reads negative 1.645. Take a look at the very first asterisk here. And if you go at top, you see 0.04 and 0.05. So it's between the two. That's why negative 1.645 gives you the area to the left as 0.0500. If you look at the second asterisk, okay, the top one, this one is between, look at the top, it's between 0.07 and 0.08. Everybody can see 0.07 and 0.08. It's between the two. So if you look at this asterisk, negative 2.575, that gives you 0.0050 to the left. Now, those are negative z-scores. And the next table, positive z-scores. Again, it's area to the left. Don't forget it's area to the left. Notice what happens. Let me just look at those two asterisks that was mentioned. Negative 1.645. Area to the left is 0.05. Negative 2.575. The area is 0.005. And by the way, don't mix up the area with z-scores can be negative or positive. And so when we look at positive z-scores, notice what happens. Look at those asterisks. We are changing the z-score to positive, 1.645. So area to the left is 0.95. Understand what happens. Area to the left is 0.95. So what is area to the right of 1.645? 1 minus that. This is 1.645. And the area to the left is 0.95, but the area to the right of this number, is the same as the area to the left of this number by symmetry. Now take a look at the area to the left of negative 2.575, 0.0050. 0.0050. Now to the right of positive 2.575 must be the same. Check this out. This one is what? To the left of it. If you subtract this number from 1, you get the same number, 0.005, area to the right of 2.575. So the idea is these two areas are the same. Just if this is the z-score, which is negative, for example, let's say z equals, let's make it up, minus 2.1, and this is the z-score of positive 2.1, the area to the left of z equals negative 2.1 is the same as the area to the right of z equals positive 2.1. So that is in case you need to read the table and get comfortable with it. We are looking at normal distribution, specifically SND, standard normal distribution, in which case mu is 0, sigma is 1. We've already mentioned the meaning of Z being between A and B. The probability of A is less than Z less than B denotes the probability that Z scores is in between A and B. And the rest is obvious. So we want to find the area to the left of Z equals 2.06. You should always start with the graph. And now you can look up a table. Those of you who have access to the table, see if you can find this, or maybe we go through that, then I will show you. Just I want to make sure that we are comfortable with that. So you go to the z-score, which is positive z-score, and you look for 2.06, and the number that gives you should be 0.9803. I'll show you with the table in a moment. The area to the right of negative 1.19. Again, you do the graph, and you can read the area to the left using the negative z-score, the left of negative 1.19, and subtract it from 1. You can also read the area to the left of positive 1.19. That gives you the same answer. And so it ends up being 0.8830. So that's how you come up with the answer if you want to use the table. We'll go over that in a moment. And also technology, whatever technology you use is fine. For example, for a TI calculator, you use those in the order. Second, var stands for variables, normal CDF, and then you put 4 entries, the left bound, right bound, mean, standard deviation, you come up with the answer. Now, one of the things is important when you want to put the numbers. If you look at the very first one, for example, there is no left bound. So, and remember, it continues indefinitely on both sides. So really the left bound is minus infinity, if you will. However, if you pick a big number on the negative side, like minus 1,000, really will do the job. On the other hand, if you look at part B, it goes indefinitely on the right side. If you large number on the right side, it will do the job. And so 1,000 would be a good choice. You don't have to stick with 1,000. Just for the sake of argument, if you use 10,000, it works fine. If you use 900, it works fine, because generally speaking, within 3 standard deviations, we cover 99.7%. I want you to know that. So use a large number, it will do the job. Look at the lower point. The lower bound, I have used negative 1,000. And by the way, make sure you do not mix up the negative and a minus sign, two different things. And the upper is 2.06. And again, you can change the negative 1,000 to any number you want, as long as it's a very, very small number. On the left, minus 900 will do the job, minus 10,000 will do the job. Mu is 0, sigma is 1, paste it, and you have the answer here. I have 2 of them, parts A and B, at the bottom also. Let's see if we can do this using a table. So 2.06, so this is positive z-score. So you're looking at 2.06. So 2.06, so everybody can see the 2.0 and then 0.06, and that is the bottom one, by this one. 0.9803, reading it from the table. So that's 0.9803. Now we are looking at negative 1.19. Let me show you how we do that, 2 different ways. Negative 1.1 here, and then we are looking at 0.09, and the answer is 0.1170. So what you're really looking at is the area to the left of this number. So how do you arrive at the answer that you want? 1. So what we want is this area. So 1 minus this number. 1 minus 0.1170, which is 0.8830. Or look at the red area, look at the blue area. We want the blue area. This number was negative 1.19. Now, if you look at the area for the positive z-score all the way to positive 1.19, in one shot you have the answer by symmetry. So let me go down and show you the positive z-score. So let's go to positive z-score. So we are looking at positive z-score. So 1.1, 0.09, and right in front of it, this is the answer without having to subtract 1. Why is that? This represents the following: the area to the left of positive z-score of 1.19. And so that's how you arrive at it if you want to use the table. It is faster to use the fact that they are symmetric, and therefore you go with positive 1.19. You can get to the answer. All right, let's do this as far as a calculator is concerned. So second var stands for the variables. Bring it down to number 2, normal CDF. Okay, lower. Now, negative 1, just put any number, that's good enough. But let's put minus. Let me change the number just on purpose. Okay, you see minus 1,000 here, class. Okay, you see minus 1,000. But on purpose, let's change it to 900. That's good too. So I'm looking at part A, z is less than 2.06. So the upper is 2.06. Mu is 0, sigma is 1, enter, enter, and you get to the answer that we had here, by the way. Notice is 0.9803. Then even if you use minus 900, makes no difference, because as I mentioned, within 3 standard deviations away, we cover just about everything. And for the next one, second was normal CDF. Again, we are using now for P is for the second one, the probability of z larger than negative 1.19. So now the lower limit is negative 1.19. The upper limit, again, I'm going to change it on purpose. Again, just use 1,000, but let's just use 1,200. I hope you understand why I'm doing this. I'm doing this on purpose to let you know we want a fairly large number, and you get to the answer, 0.88297. And if you do the rounding, you come up with the same answer. All right, we're going to move on to the next example. I want to make sure that we are comfortable using tables and technology. First, graph. I can't emphasize this enough. The graph helps you have an idea what you're doing. So in essence, we are interested in the probability between the two values. And so with that being the case, all you have to do, look this up from the table by looking both numbers and subtract the area to the left of negative 1.37 from the area to the left of 1.68. I'm showing you the technology, how we use that. The next one, the area from 0 to 2.32, that's what we want. The area from negative infinity to 2.32 is 0.9898. In other words, this one, this represents this area. And then you subtract the left side, which is left side of the zero score, which is 0.5. One other way that you can do this, dealing with the table. Look at this method. I'm going to put it up here. Now this area, this is number negative 2.32. This area is of interest to us because it's the same as the shaded region from 0 to 2.32. So you can read this area from the table of negative z-scores subtracted from 0.5. I'm telling you various methods of handling this. So find the area to the left of negative 2.32 and then subtract it from 0.5. It gives you the same answer. I highly recommend you guys try this on your own so you get familiar with different ways of approaching the table. So here's the next one.
Using the same bone density test, normal distribution mu equals 0 and sigma equals 1, find A, the probability that a randomly selected person has a result above -1, which is considered to be in the normal range of bone density readings, and B, a bone density reading between -1 and -2.5 indicates the subject has osteopenia, which is some bone loss. Find the probability that a randomly selected subject has a reading between -1 and -2.5.
And the short for normal distribution. Part A is asking for P of Z larger than -1. I would draw something like this. Z equals -1, and you want the area to the right. Okay, this area. That's it. So do a drawing, doesn't have to be to scale, but it will help you see that even if I don't have the answer, I know for sure it's larger than 0.5. And that's the idea, because to the right of it is 0.5 and we have more. And so 1 minus 0.1587, and that's using the table or technology. It is absolutely up to you. So the probability of randomly selecting someone with a bone density reading above -1 is about 84.13%, which means 84.13% of people have bone density levels above -1. All right, so above -1 is considered normal, and 84 seem to have a normal bone density. The next one, between -2.5 and -1. So again, let me just quickly graph this for you. We're going to go from -2.5 to -1, and we are interested in this shaded region. That's the idea. You go read it from the table and subtract area to the left of -1 minus area to the left of -2.5. Interpretation. There's a probability of 0.1525 that a randomly selected subject has a bone density reading between -1 and -2.5, or 15.25% of people have osteopenia, weak bones. That's the idea. It's not the same as osteoporosis. Weak bones with bone density reading between the two numbers. Now, we're going to switch gears. We found the area. Fine. What if we want to go back? In other words, the area is given, and we want to find the z-score. So we want to look at the reverse process, if you will.
Draw a bell-shaped curve and identify the region under the curve that corresponds to the given probability. If that region is not a cumulative region from the left, work instead with a known region that is a cumulative region from the left. Use technology or the z-table, find the z-score. With table A2, use the cumulative area from the left, locate the closest probability in the body of the table, and identify the corresponding z-score.
So in short, use the table or technology. Either way, you can find the answer.
Critical value. For the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. Notation. The expression z sub alpha denotes the z-score with an area of alpha to its right.
Let's see what we mean by that. Find the value of z sub 0.025. This is a notation that subscript is known as alpha. That's the alpha in the expression. So first, I want to explain the meaning of that. Okay, so you're looking at this concept. The area to the right is 0.025. That's the meaning of this notation if it's given in this format. So first, the meaning of a notation.
The notation of z, and I can't remember how to say it, a 0.02.
Z sub.
Z sub 0.025 is used to represent the z-score with an area of 0.025 to its right. Note that the value of z equals 1.96 has an area of 0.025 to its right, so z sub 0.025 equals 1.96. Note that z sub 0.025 corresponds to a cumulative left area of 0.975. Caution, when finding a value of z sub for a particular value of, and then what do you say?
Alpha.
Alpha. Note that alpha is the area to the right of z sub alpha, but the table and some technologies give cumulative areas to the left of a given z-score. To find the value of z sub alpha, resolve that conflict by using the value of 1 minus alpha. For example, to find z sub 0.1, refer to the z-score with an area of 0.9 to its left.
The idea is understand what the question is asking and understand how the table works and understand how the technology works. That's the idea behind that. So for example, when you want to look, this one is, which is 0.025, you really need to understand this area all the way to the end is 1 minus 0.025, which is 0.975. And you need that so you understand how you come up with the answer. So to find the z-score, locate the cumulative area to the left in the table. So you have to locate 0.975 in the body of the table. The table you just looked up. In the body of the table, you look for 0.975. I'm going to go over that in a moment. And if you want to use a calculator, take a look at, again, the information at the bottom right. You use inverse norm, which means normal, and you put 3 entries. So see how it works. You put inverse norm. How do you find that? Again, second and variables. You put 3 entries, the left area, 0.975, mean and standard deviation, and it gives you those answers. By the way, by symmetry, if the area to the right of 1.96 is 0.025, by symmetry, the area to the left of negative 1.6 is also 0.025. So let's see if we can quickly look at, okay, so here we are looking at the z-score, and what we are looking for, the area to the right is a 0.025. Now, first and foremost, it is easier to go to the -1, and area to the left is 0.025. Remember what we want. We want the area to be 0.025. So I'm using the symmetry on the left side and answer the question. So with that being the case, in the body, not the left column, not the top row, in the body, I'm looking for 0.025 or a number close to it. Okay, so let's see where we can find this. 0.025. Now let's do the reading. -1.906. So if I'm reading the table, I would take the easy way out by using the symmetry. And I would read just 0.025, and it gives me -1.96. So I hope you can see the negative. Since I wanted a positive z-score, the area to the right was 0.025, then by symmetry, the answer would be +1.96. If I want to go with a positive z-score, then I can't look up 0.025. Instead, I got to look up 1 minus that. So I got to look up 0.975. So for a positive z-score, I'm looking for 1 minus 0.025. That means I'm looking for this area, 0.975. And now I do the reading. I see 1.9. I see 1.9. Up here, 0.06. There you have it. So that would be dealing with the table. And let's turn this on. Clear second variables. We move down to the third one, and we want the area. We decided we have to go with 1 minus 0.025. So 0.975, and it gives you the answer. 1.95996, and it continues for a number of decimals using technology and table. So let's quickly look at the last question.
Find the z-value such that the area under the standard normal distribution curve between 0 and the z-value is 0.2123. Find the 10th percentile.
We want the following. Probability of z being between 0 and some z-value we don't have. So this is what we are looking for. It's given as 0.2123. So that means here's the graph. From 0 to some number, the area is 0.2123. How do we look it up? One easy way, remember, if you go with the positive z-score, it goes all the way from -infinity to the z-score. So you need to add 0.5. You need to add this area. And so you add 0.5. I hope everyone understands why. This is for the sake of reading. And you go to the table. In the body, you look for 0.7123. And according to this, the answer would be 0.56. Or you can use the technology as it was discussed, using inverse normal distribution. Now, in this case, what's going on when we say find P sub 10, or the 10th percentile? So that means the area to the left must be 0.1. If we were to graph something, the idea of this concept, this area is equal to 0.1, and this z-score is missing. That's the meaning of that. So if I'm trying to find this, number one, I'm going to do my graph. I'm going to do the graph so I understand what I'm looking for. So with that being the case, look at the table, look at the graph. We are interested in this portion being 0.01. I'm assuming everybody can look it up somehow using a table or technology to come up with this answer. Understand the area to the left is 10% or 0.1 because we are looking for P sub 10, the 10th percentile. We are continuing with the topic of normal distribution. We're going to look at applications of that. So we already discussed standard normal distribution. What matters to remember is that mu is 0, sigma is 1, and short S and V. And is calculated as x minus mu over sigma. The way you can calculate You can use a calculator is given here. And now we're going to move on to the new section. We are dealing with applications and we need to convert to standard normal distribution SND using the formula z equals x minus mu over sigma. So the area in any normal distribution bounded by some score x is the same as the area bounded by the corresponding z-score in the standard normal distribution. For example, if we sketch a normal curve, label the mean and specific x values, and then shade the region of interest, we have a boundary as far as the x is concerned, and we use technology or the table to go to the z-score. As we make that movement, we are using z equals x minus mu over sigma, we get to the same answer. But remember what the area represents. The area represents the probability, and more importantly, how is the area calculated? It is calculated using integration. It's a very long and tedious process. And so that's why there are infinitely many different normal distributions. The moment you change mu or sigma, you have a new normal distribution. But imagine all of them can be transformed into standard normal distribution, and all you have to do, use standard normal distribution and calculate the area under the curve. And that's why it is popular to use it in that fashion.
Heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a shower head at 72 inches.
What is given? So you read the question, you see that it's normally distributed. You see the mean, you see the standard deviation. You use symbolic format. Mu 68.6, sigma is 2.8. We want to know the percentage of those men that are taller than 72. Probability of x larger than 72. We have to go to the z-score and standard normal distribution. This is what we want. And I don't normally even graph this. I want you to know that. Instead, I find the z-score first. Z equals x minus mu over sigma. 72 minus 68.6 over 2.8. And that gives us 1.2143. For the sake of table, you can stick with 2 decimals, or you can go in between, meaning between 1.21 and 1.22, okay, because it's almost in between. And that's actually a better idea. But in any event, now that you have the z-score, look at the bottom left. Mu of 68.6 inches corresponds to z-score of 0. And x of 72 inches corresponds to z of 1.21. So this is what I mean by graphing. If I'm graphing, I rather graph with the z-score. So instead of using mu equals 68.6, I would use z equals 0. And then instead of 72, I would use z equals 1.21. And I look it up from the table. Take a look at this one again. You can come up with the area. I would rather use just the z-score. In other words, I wouldn't even bother to do this or even this. I would write 0 here. I would write 1.21, and this is my shaded region, and I look it up. This is what I would do. This is the fastest and easiest way to handle this. Now, technology, z-table, as you can see, the numbers are different. And this is using normal CDF. You can write, I mean, again, with the technology, even without changing it to a z-score, you can get it. I highly recommend you always do it, change it to a z-score, because you'll be asked to do so. And the reason the numbers are different than the z-table, remember the z-table has limitations, and the limitations would be to use 2 decimals. But even with that, if you pay attention to the fact that this number is between 1.21, and 1.22. So you look up both of them and you go somewhere in between, then it will become very close to what the technology gives us. All right, let's go to the next example.
Assume that women spend on average $146.21 per month on beauty products with a standard deviation of $29.44. Find the percentage of women who spend less than $160. Assume the variable is normally distributed.
We read the question and we need to see what is given. So very carefully as we read it, the very first thing we want to make a note of, okay, ND, we are dealing with normal distribution. Mean, sigma, the standard deviation, sigma. So that's the first thing, what is given to us. We make a note of it. And so what we want, find the percentage of women who spend less. If you have X less than 160, if you have X less than 160. Practically we're done because we understood what the question is asking. So all we have to do is to go from X to Z, table or technology, find the answer, you're done. Okay, so X is less than 160. So with that being the case, this is what we're looking for. We find the Z score, X minus mu over sigma. Now, 0.4684, you round it to 2 decimals for the sake of the table. Now, again, I would not bother with this. Instead, I would graph this one. Again, understand the meaning of it and why I have both of them for you, because I want you to understand what's happening as far as, dealing with X versus the Z score. But if I'm graphing to help me read from the table, I would graph the Z score from negative infinity to 0.47. So that means I'm looking for probability of Z less than 0.47, and we can find the answer either from technology or the table, and it is absolutely fine how you arrive at it. All right, we're going to go to the next one. We want to find values from known areas or probability or percentage. Graphs are extremely important for visualization, understanding and successfully working with normal probability so we can find the answer. With that being the case, don't confuse the Z-score and areas. Those are two different things. Z-scores are distances along the horizontal scale, but the areas are regions under the normal curve. Z-table lists Z-scores in the left columns and across the top row, but the areas are found in the body of the table. It's extremely important not to confuse the two.
Choose the correct right-left side of the graph. A value separating the top 10% from the others will be located on the right side of the graph, but a value separating the bottom 10% will be located on the left side of the graph.
If you remember when we did the P10 as an example, if we are looking at the 10% and 10 percentile only, that means the bottom 10% versus the top 10% or top 5%, and you name it.
The Z-score must be negative whenever it is located in the left half of the normal distribution. Areas or probabilities are always between 0 and 1, and they are never negative.
Here's the next example.
When designing equipment, one common criterion is to use a design that accommodates 95% of the population. What would be the maximum acceptable height of a woman if the requirements were to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. Assume that heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. In addition to the maximum allowable height, should there also be a minimum required height? Why?
We are looking at an application, so let's see what's given. Immediately we notice it is normally distributed. Here's the mean, here's the standard deviation. So it's ND, normally distributed, mu is 63.7 inches, and sigma is 2.96 inches. So those are the given we should recognize immediately. find the 95th percentile. So it's looking at the concept of an area. In other words, this is what we want. The area to the left of some number, x, is supposed to be 0.95. So to do that, the very first thing we do, we ignore the x and we assume it's a z and deal with the z, then we go to x. But for now, probability, again, we deal with standard normal distribution. Z less than some number must be the area of 0.95. And you have to look up the table or just use the technology. And it's a fairly common value. It's one of those values we should know. Looking up the table or technology, even the table has this number. Do you remember the asterisk when I went over the table? You can look it up later on. Z becomes 1.645. So what is missing? X. What I'd like you to see here is that Z score is given as X minus mu over sigma. If we do the cross product, this is Z over 1. So if I do this cross product, 1 times X minus mu is equal to Z times sigma. And you can use negative mu, take it to the other side, make it positive mu, and you get X equals mu plus Z sigma. In other words, given the fact that Z equals X minus mu over sigma, the cross product results in X being mu plus Z sigma. That's a very simple case. Now you have a mu, you have Z, you have sigma, put it in, and it gives us the answer. And the answer can be found here or in this format. You can use the inverse normal distribution using TI. So technology gives you an answer. The table gives you a slightly different answer, very close. And a requirement of a height less than 68.5 inches would allow 95% of women to be eligible as US Air Force pilots. There should be a minimum height requirement so that the pilot can easily reach all controls. So I think having a minimum value makes sense also. And also I'm showing you the Excel technology in case you use that. So this is for those who are interested in various technologies. You can always look them up. If you have access to any of them, that's absolutely fine. TI or Excel or Minitab, or there are more stat disks. Let's look at more examples.
Assume American household generates an average of 28 pounds of newspaper per month for garbage or recycling with a standard deviation of 2 pounds. If a household is selected at random, find the probability of its generating between 27 and 31 pounds per month. Assume the variable is approximately normally distributed.
Let's see what is given. So the very first thing we are looking for is this, ND. So if it's normal distribution, we need the mu. And then we need the standard deviation, which is given. See, so that's the very first thing, understanding the given. Now it says between 27 and 31 pounds. So we want between 27 and 31. So X is between 27 and 31. So all we have to do, now go to the Z-score, everybody. Go to the Z-score. And to do that, remember Z is what? X minus mu over sigma. So you have to use the Z equals X minus mu over sigma. You know mu, you know sigma, and plug in number 27, plug in number 31, and calculate the Z scores for both of them. There are values, negative 0.5 and positive 0.5. So now the graph really is referring to the Z-score from negative 0.5 to 1.5. That's what we want. So you go through the process to find this. As far as graph, you can even wait until we have, and using the Z-scores, okay? You don't even have to graph it with the X-scores. In any event, you look it up, I'm assuming everybody can look up the answer, and it's 62.47%. That would be the answer to this question, 0.6247. So if a household is selected randomly, the probability of generating between 27 and 31 pounds per month, that's 62.47%. That's horrible. So what can I tell you? Take care of your environment. Again, statistically, this is a proof that you gotta, watch out for the future, and I mean that. So let's move on.
To qualify for a police academy, candidates must score in the top 10% on a general abilities test. The test has a mean of 200 and a standard deviation of 20. Find the lowest possible score to qualify. Assume the test scores are normally distributed.
Let's see what's given. Normally distributed, mean, sigma, or standard deviation. So immediately you have to recognize those and say, okay, this is the given. So what is the question asking? That's what we want to know. The question is, we want the top 10%. So the idea is the top 10%. That means we want the probability of Z larger than some number is 10% or 0.1. We find the Z, we go to X, and we're done. So to do that, that's the idea. And again, for now, we really have the Z. So this is 200, X is missing. So we can find the Z then using the Z score such that the area is 0.1. So look at this table, and 0.8997 and 0.9015. The first one is the closest. You can use 1.28, or look at the table, use 1.285. This one is 1.29. This one is 1.28. So we can go in between. Needless to say, the left one is closer. You can say 1.284 or 1.285. That would give you a better approximation. And if you're using technology, you will get a different answer. X, we've already shown that when Z is 1.28, the formula for X is mu plus Z sigma. I went over the cross product and replaced the mu with 200, replace the Z with 1.28, I would say 1.285. And you will get a different answer there when you do 1.285. Try that.
For a medical study, a researcher wishes to select people in the middle 60% of the population based on blood pressure. If the mean systolic blood pressure is 120 and the standard deviation is 8, find the upper and lower readings that would qualify people to participate in the study.
Normally distributed. Mu is 120. Sigma is 8. We want the middle 60%. That means right smack in between is mu, then we have 30% on each side. In other words, this is the graph. The total of 60% means 30% on each side of mu means this. Probability of X between the two numbers is 0.6. So what does that mean? You can look for probability between the number and Z score of 0. Remember that you have to calculate that, and it can be done. Is 0.3, look up the table and come up with the answer. So remember this area, if you're dealing with the Z score, this area, 0.5 minus 0.3 or 0.2. So this area, pay attention to this area is point. Why are we using this point, this area? Because of the reading. So you go to the table, you want the area of 0.2, and you read the Z score. I want to erase that because I'm going to put the Z score in a moment. So you want the Z score. From the table, you read negative 0.84. You don't have to read the positive Z score. It's by symmetry, the positive value. So again, from the table, everybody, use a different color here. From the table, using this area, you get this one. From this graph, you have an area of 0.2 to the left. You go to the table and you find a Z score of negative 0.84. By symmetry, the other one is positive. And so Remember, what's x? X is mu plus z sigma. You have mu, you have sigma, you plug in negative 0.84 instead of z, that gives you a value. You plug in positive 0.84 for z, and that gives you a different value. So that means it's between the two numbers 113 and 127.